Hi everyone, and welcome to the lecture focusing on aerodynamic sources of sound. In the previous lecture, we highlighted the importance of the propagation of sound through a medium. We already know that from vibrations and musical instruments, sound can be generated by actively moving the fluid, as for example through a vibrating string of a guitar. Today, we are going to see how a sound source can be generated within the fluid itself. One of the main doubts that we might have is that the fluid where the sound propagates is the same fluid in which aerodynamic sources are generated. Additionally, our mechanical systems work within the same fluid. Think about an airfoil, for example, a wind turbine blade, or the flow of a car passing by. So how can we clearly separate between the region where aerodynamically something happens from the one where sound is just propagated? Well, long story short, this is the job of aeroacoustics. The problem can be often simplified, since most of the aerodynamic pressure fluctuations have scales and speeds that are very different from the acoustic ones. For example, even for an object as big as an aircraft, you can think that the noise propagates way beyond the region where the flow is perturbed by its aerodynamic flow. Therefore, at this stage of your learning, let's simplify the problem by dividing the flow into two regions. One where we have aerodynamic fluctuations of pressure related to the displacement of fluid, and the other one where we have propagation of acoustic waves, therefore acoustic pressure fluctuations. Remember, this is just a first simplification to get you started. We are going to focus now on the source region. We are going to study first, from a mathematical point of view, how certain aerodynamic processes determine the source term of our sound wave propagation. The theory we are going to study was originally developed by Sir James Lytle in the 1950s. In order to describe how the flow can generate sources of sound, we first start with the mass and momentum conservation laws in fluids. Let's start first with free flows, neglecting external forces and mass injections and ejections in your domain. No worries, we will add them later. Viscous forces and small turbulent fluctuations will be taken into account. The mass conservation or continuity law presents the variables ρ and the velocity components in Einstein's notation VI Vj. Even if you don't recall the formalism, it basically highlights that in every point of your volume, every infinitesimal increase or decrease of density flux must be balanced by a local change of density. Or equivalently, if you bring more mass in than out in a control volume, then your flow density should change. At the same time, the momentum equation states that the rate of change of momentum of a fluid element, indicated by the time and space derivative of the ρ and VI Vj terms, is equal to the sum of the pressure forces P' and viscous forces sigma ij. What we want to achieve is to rewrite this equation by having the formalism of a wave equation with aerodynamic sources on the right side. By making this possible, we understand how aerodynamic phenomena can create an acoustic response. Now, this is where it gets tricky. There are several steps to rearrange the equations, but we will make them as easy as possible for you. First three steps are basically needed to combine the two equations in one. To do that, we get the time derivative of the first and the divergence of the second, and we subtract the two. What we get is already very close to what we need. We see that the double derivative of the density fluctuations are related to the spatial variations of the previous aerodynamic terms. Step 4 is applying the small perturbation analysis. What it means is that we are not interested in mean aerodynamic or acoustic values of our variables, but just on the time development. So what we do is to remove from every variable, density, pressure, etc., their mean values, also because their spatial and temporal derivatives are constant. Step 5 is just cosmetic. We subtract the Laplacian of the density fluctuations multiplied by the speed of sound squared. And we made it. What we got is the non-homogeneous wave equation, describing on the left side the propagation of acoustic waves, and on the right side the aerodynamic source terms, including turbulent stresses, viscous stresses, and nonlinear pressure. Note that for mathematical rigor, all the primes should be still indicated for all variables. For example, the components VI and VJ are turbulent stresses because their mean has been removed. But historically, the primes are kept only for the components most visible in the wave equation, more for an aesthetic link to acoustics than for other reasons. So once again, we reached our target. On one side, the acoustic propagation, on the other side, the aerodynamic source term. You might find in literature the same equation written with pressure fluctuations, but as you can see, the theory is the same. That means that for specific aerodynamic processes, an acoustic wave is generated and propagated to the surrounding. This is interesting because we can now ask ourselves, what are those processes? Well, if you have a look back at our hypothesis, in absence of external forces or mass injection and ejection, the fluid can still require the propagation of information at the speed of sound through its own domain if non-isentropic effects are present, as turbulent, nonlinear pressure, or viscous stresses. This kind of sources have a quadrupolar distribution due to the double derivative form, and we will see this in the next chapter of this lecture. Let's summarize and go back to our first concept. From a mathematical point of view, the wave equation prescribes how sound waves move in space and time in a medium. In presence of the source term, the propagation is related to the sound generated by the precise source term. From an aerodynamic point of view, we have seen that in a region where turbulent, nonlinear pressure and viscous stresses are not negligible, a source term arises for the propagation of acoustic waves. We can give you a small exercise, this time neglect viscosity, turbulent stresses and nonlinear pressure stresses and try to follow our previous steps by including a mass injection or ejection term and an external force field. You will come out to this new equation where two additional sources of sound are now present. These sources, as we will see, are derived from external actions on fluid. As a quick recap, your aeroacoustic journey starts from identifying a source region in the vicinity of the object where the aerodynamics of the systems you are analyzing cannot be neglected. In this region, sources of sound can be created by very precise aerodynamic processes, internal or external to the fluid. In the far field, the sound is just propagated as an acoustic wave, and you can neglect aerodynamic flow variations. Have a look at this aeroacoustic simulation now, where fluctuations of pressures are color-coded. Can you visually identify these two regions? In the first part of the lecture, we derived three different source terms of the wave equation, but is the sound propagation always the same for all these sources? Let's focus on the last two sources. We saw that an unsteady injection of mass is a sound source, and the divergence of a force field is also a sound source. The first is proportional to the time derivative of our entering or exiting mass. The second on the spatial derivative. Qualitatively, we would expect that the sound is propagated in all directions from the source. If the source has no spatial variation, the sound should also propagate with no spatial variation, and vice versa. And that's exactly what happens. With no variation in space, the source of sound is called monopolar, usually spherical. While with one single variation in space, we obtain a dipolar contribution. Monopolar sources have a spherical sound propagation which decays with 1 over the radial distance. They are the most efficient radiator, that means the loudest for the acoustic energy they have. And some typical examples are the unsteady mass injection of a siren or everything that obliges the flow to eject from a specific region, such as the sudden passage of a rotating blade due to its thickness. Dipolar sources have a directional response. They are a bit more complex since they are the superposition of an acoustic near field, which decays faster with the radial distance squared, and an acoustic far field, which decays with 1 over r. They are less efficient than a monopole, as you can also see from the color coding. Our acoustic examples are typically derived from everything that creates a fluctuating force field, such as rotating blades, but also shedding on aerodynamic objects. If one spatial derivative creates a dipole, now you can better understand how a double derivative can create a quadrupole. To summarize, monopolar contributions are associated to mass injections. Dipoles are derived from divergence of a force field. Quadrupoles are generated by the double derivative of the lightly turbulent stress tensor. At this point, we have treated all possible sources in the flow due to the flow. But what happens when surfaces and other objects are involved? The mathematics becomes pretty complex, since mathematical tricks would be needed to be used to introduce the effect of surfaces in the flow. The final equations become massive. If you are interested, you can have a look at the Fock-Williams-Hawking derivation in our course. In summary though, the physics does not change. In presence of moving surfaces, additional monopoles and dipoles are generated by the fluid that needs to be displaced due to the presence of a thick and possibly moving surface, and by the variation of the field generated by the variation of the aerodynamic parameters on top of the again possibly moving surface. Let's try to be more practical and see what happens when we consider that in fact our surfaces amplify the scattering of our aerodynamic fluctuations as additional dipolar contributions. As we have learned before, in absence of surfaces, the acoustic pressure fluctuations will be determined by the lightly turbulent stress tensor source. If we consider just the turbulent part and we solve for the acoustic energy proportional to the p prime squared, we can see that the value is proportional to the local Mach number to the power of 8. When it is close to a surface, the radiation changes to the power of 5/6. Now, since the Mach number is mostly between 0 and 1 for conventional application, this means that the dipoles will be stronger and more efficiently radiating. Whether the power is closer to 5 or 6 depends on the relative size of the surface with respect to the aerodynamic fluctuations. The Helmholtz number comes to our help, since it is a dimensionless quantity used in acoustics to determine how acoustic fluctuations and wave propagation occur, often related to the acoustic compactness of a body or domain. It is defined as the ratio of a characteristic physical length to the acoustic wavelength, or as the product of the wave number and the characteristic length. A small Helmholtz number indicates an acoustic compact object, while a large number suggests that the object size is comparable to or larger than the wavelength, leading to complex acoustic behavior. So, in case you expect a dipolar source due to fluctuations of turbulence close to your object, it is a good practice to calculate the Helmholtz number associated to your object and to the size of the aerodynamic vortices or boundary layer turbulence you expect, approximately in fact. If this is way less than 1, you can expect a perfect dipolar contribution deploying mostly from the most discontinuous part of your object, the edge of your object. If it is larger than 1, then you can expect an inclined dipolar contribution with higher radiation in the direction of the incoming flow and a different scaling of the acoustic power with respect to the speed of the flow. It was a long lecture. Let's close it here for the moment, have a look again at the slides, and use the additional material if you have further curiosities. Thanks for listening, and see you next time.